So we're going to look at graphing inverse trig. So yesterday we graphed the basic ones. But what happens if we change it up a bit? So for instance, something like this. Y equals 5 inverse sine x on 3. It's pretty much going to be the same inverse sine shape. All that's affected here is the domain and range. So what I tend to do is work out the domain and range first. So normally I would have inverse sine x. But this time we've got inverse sine x on 3. So the x on 3 will go in between minus 1 and 1 instead of x going in between minus 1 and 1. Well, that tells me then that x must go in between minus 3 and 3. Then I do the same thing with the range, but I've got to be careful. Because I'm dealing with range, this 5 out the front of the inverse sine, I need to group with the y. So I'll actually say y on 5 will go in between minus pi on 2 and pi on 2, which tells me y goes in between minus 5 pi on 2 and 5 pi on 2. And then I can pretty much draw the same graph as I did before. I've only got to change the numbers. So instead of putting minus 1 and 1, I'll put minus 3 and 3. And instead of putting minus pi on 2, I'll put minus 5 pi on 2 and 5 pi on 2. And then I can draw exactly the same graph. So y equals 5 inverse sine x on 3. So that's how we can deal with the basic curve, and we've only changed the domain and range. What about something like this? The inverse tan of the square root of 3 minus x squared. All right, well, I'll do it the same way. The domain was, well, for inverse tan, it's all real x. So it was saying I could substitute anything into inverse tan. However, I'm not just substituting straight into inverse tan. If you think about it like grouping symbols, before it gets to the inverse tan function, it has to go into the square root function. And that has its own problems, because you can't find the square root of a negative number. So we've got to look after that first. So 3 minus x squared will be greater than or equal to 0. So I know x will go in between minus root 3 and root 3. That's now going to change the range, because we've got our inverse tan graph, but instead of substituting in every x value, I'm only substituting x values from minus root 3 to root 3. So that's going to change where the graph stops. So if we sub in root 3, I can see I end up with 0 on that one. If I sub in minus root 3, well, I also get 0. So the two endpoints are at 0. Well, what's happening in the middle? That's usually a good thing to check as well. So in the middle, when x equals 0, I get pi on 3. So the range is going between 0 and pi on 3. So let's draw that, and we get something which doesn't look like an inverse tan graph at all. It actually looks more like, well, it's not a semicircle, but it looks more like that sort of shape. So that's a very different type of inverse trig graph. So, but again, you look at the domain and the range and see what's happening. The inverse sine of sine x, well, the temptation is to just draw y equals x, because inverse sine and sine will cancel out and we'll get x. However, again, we've got to think about the domain and range. Domain. Before I can substitute into the inverse sine, I have to substitute into the sine. So we're saying sine x is going in between minus 1 and 1. Well, sine x is always in between minus 1 and 1. Therefore, I could substitute any number I like into this and get an answer. Okay. But what about the range? Because it's an inverse sine function. I know I can only get answers out that are in between minus pi and 2 and pi and 2. So it can't be y equals x. Well, let's just draw up something here. So plot in some x values, pi, and we know it's going between pi and 2 and minus pi and 2. So, all right, we know basically it's y equals x. I'll just draw it for that little section there. But then what happens? Because it can't go any higher than pi on 2 or any lower than minus pi on 2. Well, I guess the easiest way is to just sub some points in. If I was to substitute pi into our function, well, the sine of pi is 0. And the inverse sine of 0 is 0. So what ends up happening is we actually end up getting a zigzag. So it's y equals x just for that little part, but then it'll go down and up like a sine curve, but now it is a zigzag, straight lines. Well, how will this one be any different? The sine of the inverse sine of x. So if we do it the other way around, so again, it looks like it'll be y equals x. Domain. Well, I got to substitute it into the inverse sine function first, and that has restrictions on our domain. We know the domain for inverse sine is -1 and 1. So this one won't go all the way along the x-axis. It'll only go between -1 and 1. The range, well, let's have a look at the endpoints. When x is 1, I get the sine of the inverse sine of 1. The inverse sine of 1 is pi on 2, and the sine of pi on 2 is 1. Kind of was expecting that, because we know it's got to have something to do with y equals x. What about -1? The inverse sine of -1 is minus pi on 2, and the sine of minus pi on 2 is -1. So, okay. Well, let's have a look in the middle. Oh yeah, and when x equals 0, y equals 0. So in this case, we are going to get y equals x, but it'll stop. It'll stop at 1, because the domain won't let me plot any more points in. So when it was inverse sine of sine, we got the zigzag, but when it's sine of inverse sine, we just get a piece of y equals x. So 17c is, well, manipulating the inverse trig graphs and seeing what unusual shapes we might get.